While you're standing in front of the school waiting for your ride, you watch a car move to the right. So it's moving this way up Grand Avenue. Which way does the car's acceleration point? Explain. So how do you answer this? Well, there's three choices first. So the choices are acceleration is to the right, acceleration is 0, or acceleration is to the left. So what would it mean if you chose each one of these? So if it's moving to the right, and let's say the right is positive, if acceleration is to the right, then these agree. These are in the same direction, which means it would be increasing speed. When acceleration is 0 and velocity is to the right, this means constant speed. And when acceleration points opposite the direction of velocity, it points to the left, that means decreasing speed. Well, you're just watching the car move to the right. It could actually be any of those. So any of the three would be correct. You would need more information to figure out anything else. So now we need to draw a motion diagram for the car traveling to the left, so velocities to the left, at decreasing speed. When you see the word decreasing, that tells you V and A point in opposite directions. So that means acceleration is this way. So you can show that by showing arrows getting progressively smaller, or you can just show just that they point opposite. That would be sufficient as well. A car moving left slows to the right at a red light. Well, that's kind of the same thing. It's moving left, it's slowing to a stop, that's decreasing speed. So that means, so the motion diagram is the same. The ball is thrown upward, so it's moving up and it's moving towards max height. So so this you have to know something. As a ball moves upward, it slows down. Again, we're doing decreasing speed. That means velocity and acceleration are opposite. So these are three examples all showing decreasing speed. So velocity is opposite the direction of motion. Okay, so we're looking at these diagrams. We've looked at these before, I think. So now we're going to identify the type of motion that we see in each picture. So I'm just going to write it right next to each diagram. So this one, in all cases, it's moving from the left to the right. This arrow just shows the axis. So it's moving this way, and you can see it's increasing speed, which means acceleration is also in the same direction. This is clearly constant speed, so it's moving to the right, and acceleration is 0. So this is constant speed. This one is moving left to right, so it's moving this way and it's slowing down. So acceleration must be to the left. So this is slowing or decreasing. And this one, again, we're moving left to right because it said so. So again, we're increasing speed, so acceleration must be in the same direction. Here we're moving with constant speed, so velocity, it's got to be this way, down the hill. So these are evenly divided, right? They're evenly spaced, so this is constant speed. And this one, we're moving in this direction from left to right, and we're increasing speed. You might say, well, how could it do that? Well, it must have been given, there must be a force acting on it, even though you can't see it. So that has to be the case, increasing speed. Okay, so now we're going to rank each case from highest to lowest instantaneous velocity. So instantaneous means at the last velocity that you could find. So for this, we're going to examine the last segment of each of these. So we're going to look at this segment, this one, this one, this one, this one, and that one. And you may find it useful to take out a ruler, and we'll assume that it says to assume that the distance scale is the same. So if I just use a ruler to measure this, and my distances may come out a little bit different than yours, just because if you don't print it, you might have on your screen, it may be different. But my measurement, this is 1.8 centimeters. B, this I'm doing from center to center, by the way, is 0.3. C is also 0.3. You might be asking yourself, why is she measuring the distance? This is 1.8. You don't have to. You can do this visually if you trust that your senses are good enough. to see whether things are the same or not, then that's perfectly fine. But I prefer quantitative when I have access. So you can see that for this last position, right, this last interval, they're going the same, right? And these are all during the same time interval. And when you find velocity, it's always the displacement over the time. So if the time interval is the same for all, right, this is same for all, then what's going to tell you about the velocity is the displacement. So you can see that the displacement of A, D, and F are equal, and that they're greater than B, which is equal to C, which is equal to E. Now, this would be the speed. Okay, I just ranked the speed. Now, that whether they're equal or not, we also need to look at the direction. So I kind of neglected this, so I have to go back and do it because I forgot. Okay, honestly. So it said using the coordinate system specified. So look, this is moving. This one here is moving in the negative direction. So the displacement is actually negative. This, the positive, is to the right. So that's positive. Here, it's moving up. It's moving in the negative direction, opposite. This one is moving in the negative direction as well, right? It's opposite. Which way is positive? This one is moving in the positive direction. And this one is moving in the positive direction. So now, right, if I was going to rank the velocities, I would do this differently because I got to take into account the signs. So F is biggest, then B and E are next, and then C is next, and then A and D. So the difference between ranking speed and ranking velocity is that speed is independent of direction. You don't worry about the signs. So you could ignore the signs. Velocity, the signs matter. Okay, so as long as, even if you see this, this is just practicing, do I understand when to make things positive or negative? Now, in terms of ranking from highest to lowest magnitude of acceleration, well, that isn't so hard, right? Because I can see a bunch of these when acceleration is 0. So I know that B is equal to E for sure. That's 0. Okay, so everything else is going to be greater. So we can see that we've got increasing speed in the negative direction for this one. So acceleration here is negative. You can just look at this arrow. Here the acceleration is negative. This one, the acceleration is positive, and this one, it's positive as well. All of these have the same interval, right? It's the same differences here. So you're going to have to just we've got our positive values, which are going to be F and C. And then the negative values are going to be A and D. So that's how you rank these. These are going to be positive acceleration. These are 0 acceleration. And these are negative accelerations. And all that you get off the motion diagrams, which makes it really nice. All right, so here's a spark tape. The easiest way to make a motion diagram from a spark tape is actually to connect the dots. So you can just go 1, 2, 3, 4, and you can get a sense once you see those arrows that acceleration must be 0. This is constant speed by looking at those. What are the signs of displacement, velocity, acceleration? So it says here that the left side is the beginning, so we're starting here. So this is time equals 0. And it also tells us that it makes a dot every 10th of a second. So this is time is 0.1, 0.2, 0.3, 0.4, 0.5, and 0.6 seconds. So the displacement is in the positive direction. The velocity is in the positive direction. The acceleration is 0. Use a ruler to find the average speed of the first and last interval. So we can do To find the average speed, its speed equals distance over time. So this is 2.15. Velocity equals distance over time. 2.15 centimeters over 0.1 seconds, which is going to be 0.21, 5 meters per second. Notice I converted it, so you can change that to meters per second. If you left it in centimeters per second, it would be 21.5 meters per second. So this is the initial. And then the final would be using the last segment, which should be the same, but let's measure. This one's 2.2, so it's going to be pretty close, over 0.1, because the difference between 0.5 and 0.6. So that'll be 22 centimeters per second, which is 0.22 meters per second. Okay, an 878 kilogram car skids to a stop across a horizontal surface. Okay, so this is about sketching, creating a label sketch. We are not solving this. We're going to label V, X, T, where X is position. This is our initial, and then the car is going to move to some final position. Sometimes I do 1, 2. You can do that also. They also give you this mass, so let's label that M, 878 kilograms. It skids to a stop, which tells me that its final velocity is 0. The distance, the initial position, initial time are almost always 0. This is 45.2 meters. The average force is given, which we don't know much about yet. We haven't gotten to that, but you can list it. This is what we're trying to find. And we don't know anything about that. And then the acceleration is also unknown, so we don't know those. I just leave them blank. You can put question marks there or whatever. Don't use the variable x. That is not something we do, right? We use x to be position. And this is where you can, the only other thing you have to do is you need to draw a motion diagram. So it's moving to the right in the positive direction. Obviously it's stopping, so it must be slowing down. So this is going to be a negative value. So this is your whole setup. Okay, let's do the next one. A 110 gram toy rocket. Oh, so you're given the mass. Let's put that into kilograms right away. It's at rest on a launch pad. So here's my drawing. So it's at rest. During the fuel burning stage, the rocket accelerates upward. So, okay, so here it is here. This is accelerating to 7.4 meters per second squared. And it does this for how long? Well, we're not moving on the X, we're moving on the Y. So I put V, T, and Y. Notice the order doesn't matter. Right, we're starting at the ground, and then V, T, and Y. We'll call this 1. We could call this 2. Like I told you, you're welcome to do that. We don't know this new position. We know this is 3.8 seconds. We don't know how fast it's going. Sometimes I'll write like greater than 0. That might be useful. You can do that if you want. And then it says the fuel burns out, leaving the rocket to continue upward due to its inertia. What is the vertical position when it runs out of fuel? So what we're looking for then is this. This is what we want to find. So we've labeled it. We're done. We don't need to do anything else for this problem. Oh, we do. We need a, we have velocity pointing up, it's moving up, and acceleration must be up because it starts at rest, and then it's going to be going fast. So both of those.